but also you can calculate the relative permittivity. So moving towards our next slide, which will show the next question which was asked during your question hours. This is the third question through which you will gain that how we can distinguish hard and soft magnetic materials. Let us distinguish hard and soft magnetic materials. In our slide, we have represented hard magnetic material and soft magnetic material. It represents that how it differs from each other. Let us start from soft magnetic materials. Why it is called soft magnetic materials? The first question is why it is soft magnetic materials. The answer for that question is it is called soft magnetic materials because on applying magnetic field, or this material can be magnetized or demagnetized easily. So they are represented as soft magnetic materials. In comparison to that, if we talk about hard magnetic materials, they cannot be easily magnetized or demagnetized. The first point represents soft magnetic materials. Soft magnetic materials have small hysteresis area. Friends, we have represented magnetic materials and we have also studied the hysteresis cycle. The area of that hysteresis cycle for soft magnetic material is smaller. If we distinguish it with hard magnetic material, the hard magnetic material have large hysteresis area. So these are the 2 points through which we can distinguish soft and hard magnetic material. Let us distinguish it with more points. Let us move towards next point. Easy domain walls movement is possible in presence of external magnetic field, whereas in hard magnetic material, easy domain wall movement is not possible. That means in soft magnetic materials, due to the presence of external magnetic field, due to the atoms and grain boundaries, the domain walls are easily movable, due to which there will be change in its magnetism. That means they can be easily magnetized or demagnetized. Whereas easy domain wall movement is not possible in hard magnetic material, which represents that it cannot be magnetized or demagnetized easily. Let us move towards the third point. These magnetic materials can be easily magnetized or demagnetized, and these magnetic materials cannot be magnetized and demagnetized. Soft magnetic materials can be easily magnetized and demagnetized, whereas hard magnetic materials cannot be easily magnetized or demagnetized. Let us move towards next point. They can be permanently magnetized. They cannot be permanently magnetized, beg my pardon. Soft magnetic materials cannot be permanently magnetized, whereas hard magnetic materials, due to less domain wall movements, they cannot be permanent, they can be actually permanently magnetized. So if we want to make a use of permanent magnet, then hard magnetic materials are the materials through which you can make it possible. For soft magnetic materials, the coercive field is very low, as well as the remnant magnetization values are very low, which are due to easy domain wall moment. Due to easy domain wall moment, the coercive field and remnant magnetization are very low. So we can say that due to less coercive field, the question arises in your mind that why the value of coercive field as well as remnant magnetization is very low? The answer is the hysteresis area when you apply the field and when magnetic flux density B is obtained, the hysteresis is generated, and the hysteresis area for soft magnetic materials is very low. That means the area is very small. So due to which we can take this point. Let us move to this slide. The value of this is low coercivity and low remnant magnetization, whereas for hard magnetic materials the coercive field is high, whereas it is having high remnant magnetization due to less domain wall movement. That means for hard magnetic material the hysteresis area is more, and if the hysteresis area is more, the coercive field will be high and high remnant magnetization. So my dear friends, if we want to distinguish soft magnetic materials and hard magnetic materials through the hysteresis cycle, the hysteresis cycle area of soft magnetic material is narrower. So due to which the coercive field and the remnant magnetization will be also low. And with respect to hard magnetic materials, the hysteresis area of the hysteresis cycle is very large compared to soft magnetic materials. So the coercive field and remnant magnetization will be high compared to soft magnetic materials, which is having a large area of hysteresis cycle. So let us move towards the next point of soft and hard magnetic materials. It has low hysteresis loss. My dear friends, if the area of hysteresis cycle is narrower, the hysteresis loss will be also very low, and compared to that, if the hysteresis loss is very less, that means the energy loss is very less and the eddy current loss will be also very less. If we move towards the hard magnetic material, the hysteresis cycle area is very large. That means what? It represents that the energy loss is higher if the area is also large. That means hysteresis loss or hysteresis energy loss is higher in hard magnetic material, and with respect to that there will be more eddy current loss in it. So this was the presentation of soft magnetic materials and hard magnetic materials. Now in this slide you can see that how soft magnetic materials are produced, or how we can make soft magnetic materials. Soft magnetic materials are prepared by heating the pure materials to a temperature at which atom can easily settle down into ordered lattice by slow cooling. What do you mean by ordered lattice? Ordered lattice means the atomic arrangement is perfect. It is having a higher order arrangement. In red words, the sentence written is annealing process. The annealing process represents slow cooling. That means the increase in temperature as well as the decrease in temperature is stepwise. That means the temperature that means it represents the slow cooling process. That means we can say that annealing process is a slow cooling process. That means atom gets time to easily settle down in a ordered lattice by slow cooling process, and with respect to this, through this process we can get soft magnetic material. In the same manner, if we compare this with hard magnetic materials, the process through which hard magnetic material produced is quenching process. Let us see the next slide. Hard magnetic materials are prepared by heating the material to a required temperature, and then it suddenly comes to cooling. That means what? If an atom is heated at a higher temperature, materials are heated at a higher temperature, due to which what will happen when we are cooling the material, there will be two processes, one will be annealing and another one will be quenching. If we represent the annealing process, it is a slow cooling process. That means temperature will be decreasing in stepwise manner. But what about quenching? Quenching represents the cooling system through which if a material is at a higher temperature, you will cool it down to very low temperature. That means if you take a material and heat it down at a higher temperature, and when you suddenly drop it into water, what will happen, friends? The thing will happen that the atoms of that material at higher temperature will not get time to easily settle down by sudden cooling. So this is the hard material through which you can represent the quenching process. That means hard magnetic materials are made up by quenching process. Let us move towards next question. Next question is the sum which is regularly asked from magnetic materials. Let us read the question first. A magnetic field strength of 2 into 10 raised to 5 ampere per meter is applied to paramagnetic material with relative permeability of 1.01. Calculate the values of B and M. My dear friends, B represents the value of magnetic field intensity, or you can say magnetic density, B, which is equal to H, and H represents the applied field. Here mu represents the permeability, mu 0 represents the permeability for free space, and mu r represents the relative permeability. So B is equal to mu into H. If B is equal to mu 0, mu r into H, what does it represents? Let me show it in the equation through this board. Let me show the equation. The equation is B is equal to mu into H. Here H represents the applied magnetic field, or you can say B represents the magnetic flux density, and mu represents the permeability. Let us write one more equation. Mu represents the permeability, which is equal to mu 0 into mu r. So if I want to substitute this value in the above equation, we can write the above equation in this manner, that is B is equal to mu 0 into mu r into H. Through this we can calculate the values of B. My dear friends, the value of mu r is given to us, the value of H is given to us, and we have to substitute the value of mu 0, that is permeability for free space, and the value of mu 0 is equal to 4 pi into 10 raised to minus 7. By substituting this value in mu 0, by substituting the value of mu r, let me write it, it will be multiplied it by the value of 1.01. 1.01 is the relative permeability, and the value of H represents 2 into 10 raised to 5. So substituting the value of this all in the above equation, this equation or this value represents only the value of mu 0. I repeat, 4 pi into 10 raised to minus 7 is the value of only mu 0. But if you substitute all this value in the above equation, mu 0 it will be 4 pi into 10 raised to minus 7, mu r it will be 1.01 into h, that is 2 into 10 raised to 5, and the value you can obtain is b. So you can write it, which is equal to b. So let us move towards our slide. Here the next point represents susceptibility. Here you can see that susceptibility is equal to mu r minus 1. Now we want to find out the values of b as well as m. How we can find out the values of b and m? Let us say it on the written board. The value of chi is equal to mu r minus 1. Here chi represents susceptibility, mu r represents relative permeability minus 1. We want to find out m. What will be the value of m? M is the value of magnetization. Dear friends, chi represents susceptibility, and the equation for susceptibility is chi is equal to m upon h. We have to substitute this equation instead of chi. So our equation will become m upon h will be equal to mu r minus 1. We have the value of mu r, we have the value of h. The thing is, we will calculate by substituting the values of h, by substituting the value of mu r, and then we can get the values of m. So through this equation we will substitute the values of susceptibility by substituting the equation chi is equal to m upon h, where m represents the magnetization, h represents the applied field. When substituting this equation in the above equation,